In this video, we are going to be learning about pressure volume work as part of our learning objective for calculating internal energy for processes and explaining the classification as a state function. Our earlier definition of work was force applied over a distance. We learned in our previous chapter unit on gases that gases can expand when heated, or chemical reactions can produce additional moles of gas, causing an expansion in volume. If the gas is contained within a cylinder with a movable piston, then as the gas expands, it forces that piston up. That is force being applied over a distance. That means that this gas is doing work on the surroundings. And so work will have a negative sign when it's doing work on the surroundings. So I'm going to write negative when gas expands. Work done on surroundings. Work will be positive when the gas contracts. Because then the system is having work done on it. So work is negative when the gas expands. But since we always calculate delta V as being final minus initial, if the final volume is more than the initial volume, then this is going to result in a positive value. But we need our overall work to be negative. Pressure is always positive, and so if delta V is also positive, then the product of these two would be positive. But we need it to be negative. And so therefore, there's a negative sign up in front. This helps make sure that our sign for work is correct. If delta V is negative, then this will make this negative sign up in front will negate the negative and make it into a positive function for work done on a system. So it's very important to remember that this sign here is to help correct this sign for delta V. We saw that our work equation was negative P delta V. The units for pressure can be any of our pressure units like atmospheres, and the volume unit would be liters. But work is a unit of energy, which is measured in joules. And so we have to be able to convert between liter atmospheres and joules. We can do that from using this equation, where we set R equal to R. Our ideal gas constant R can be expressed in a variety of different units, such as 8.3145 joules per mole Kelvin. And we can also express R in liter atmospheres, 0.082058 liter atmospheres per mole Kelvin. If I want to keep joules and cancel out liter atmospheres, then I'll divide both sides by this constant. So I'm going to divide both sides by 0.082058 liter atmospheres per mole Kelvin. Divide the other side by that as well. And so this whole side cancels out and gives you 1. The mole kelvins here are both in the denominator, so when you divide by something in the denominator, it becomes in the numerator. So those will cancel out. And so then you're left with 8.3145 joules divided by 0.082058. Lift out the 0. And then that's going to be equal to 1. We can also simplify this fraction. So let's just type that into our calculators. 8.3145 divided by 0.082058 is going to be 100.77 divided by, that's not right. So if we divide these two numbers together, then we end up getting 101.3 divided by 1. So that tells us that 101.3 joules is equal to 1 liter atmosphere. So you might see this used as a unit conversion in your homework, and this is where it comes from. So you can always use these values from your yellow sheet. Let's do an example problem. It reads, a cylinder equipped with a piston expands against an external pressure of 1.58 atmospheres. So that's my P. If the initial volume is this, that's V initial, and the final volume is this, how much work in joules is done? So it's good to just start with your equation that has no numbers in it. That way you can remember your whole equation. P is 1.58 atmospheres, so that's going to be negative 1.58 atmospheres. And then delta V is going to be final minus initial. So V final was 1.245 liters minus 0.485 liters. So our work here is equal to negative 1.2008 liter atmospheres. And then we'll want to convert that to joules because we're wanting our answer in joules. And so that's going to be 1 liter atmosphere down here. And I'll use our simplified conversion from the previous slide. And so that's going to be negative 121.67. And then I have to check my sig figs. This here is going to result in 3 after the decimal from the subtraction. And that's going to be 3 sig figs here. So 3 times 3 is going to be 3 sig figs. 1, 2, 3. And so I'm going to keep 3 sig figs in my final answer. And so the 6 will cause that to round up. negative 122 joules. It's also good to check your sign and make sure that your sign makes sense for this question. Since it is expanding, then the gas is expanding, and so your system is doing work. That means that energy is leaving your system, and so your system should be a negative value. So work needs to be negative, and the value we calculated is negative. Let's do a practice problem. Go ahead and pause your video and try to work out this practice problem on your own. Play the video when you're ready to check your work. All right, let's go over this. It says when fuel is burned in a cylinder equipped with a piston, the volume expands from this, that's our V initial, to this 1.45, which is V final, against an external pressure of this, is your P. In addition, 587 joules is emitted as heat. So that is our Q value. What is delta E for the burning fuel? All right, so before we begin, let's kind of figure out our signs for things. So we know that for work, we are expanding. And so that means that our system is doing work, and so our work should be negative. Additionally, for our heat, it says emitted. That means that this is an exothermic reaction. Heat's being emitted, and so that should also be a negative sign. We can set up our delta E equation to be heat plus work. We know that our work is going to be equal to negative P times delta V. So our delta E is going to be equal to Q, which is a negative 875 joules. And then when you add a negative, it's like subtracting. So I'm going to write minus, and then we have 1.02 atmospheres. And then we have our final volume, 1.45 liters minus 0.255 liters. And then we have to calculate that. If you did your calculation just like this, you would have had a unit mismatch. We also need to convert our work into joules so that we can subtract our units. So I have to remember to subtract to convert my liter atmospheres into joules. And I can do that by tacking this conversion on to the end of my equation. So it's going to be minus 875 minus 1.02 times 1.45 minus 0.255 times 101.3. And so that gives us a value of negative 998.47 joules. And then we have to figure out our sig figs. The subtraction here will result in 2 after the decimal point, but this 1 will still be here. That will give us a total of 3 sig figs from there. That's times 3. The subtraction here, that's only significant to the ones place. So let's see, that's 3. And then we'll multiply it by that, and that's also going to be a 3 sig fig number. So we're going to round to 3 sig figs here. And so that's negative 998 joules.